Beneath the surface of our planet, hidden in plain sight, lies a silent archive of Earth's deepest secrets. Picture this: the ground beneath your feet isn't just solid rock or shifting soil. It's a time capsule, preserving echoes of ancient earthquakes, lost civilizations, and cataclysmic events that shaped the world as we know it. These echoes, known as seismic shadows, are like whispers from the past, traveling through the Earth's layers for thousands of years, waiting for someone to listen. And today, scientists are doing just that, tuning into these subtle vibrations to uncover stories buried for millennia. Think about the last time you felt the rumble of an earthquake, even a faint one. That tremor didn't just vanish into thin air. It traveled deep into the earth, bouncing off layers of rock, bending around molten magma, and leaving behind a trail of clues. These seismic waves act like sonar pulses, mapping the unseen world beneath us. But here's the astonishing part: sometimes those waves don't behave the way we expect. They create shadows, areas where the Earth's structure bends or blocks them, leaving behind gaps in the data. And it's in those very gaps that the most fascinating discoveries are made. Imagine a detective story where the absence of evidence becomes the most important clue of all. This isn't just about geology or ancient history. It's about understanding the very foundation of our world. Seismic shadows have revealed lost cities swallowed by time, like the ruins of ancient Troy or the sunken temples of Dwarka. They've uncovered hidden fault lines that could rewrite our understanding of earthquakes. And they've even hinted at colossal events, like the asteroid impact that wiped out the dinosaurs, leaving behind a seismic fingerprint still detectable today. These shadows aren't just scientific curiosities, they're portals to the past, offering us a chance to piece together the puzzle of Earth's evolution. So, how do scientists decode these silent messages? And what other secrets might be lurking in the darkness beneath our feet? That's the journey we're about to take together, unraveling the mysteries of seismic shadows and the stories they tell. The discovery of seismic shadows wasn't a sudden eureka moment. It was a slow unraveling of Earth's hidden language, one earthquake at a time. Back in the early 20th century, scientists noticed something peculiar. When they tracked seismic waves from distant quakes, certain stations would detect the vibrations while others, positioned at specific angles, recorded nothing at all. It was as if something deep within the planet was casting a shadow, blocking the waves from reaching the surface. This baffling absence became the key to unlocking Earth's subterranean secrets. The real breakthrough came when researchers realized these shadows weren't random. They followed predictable patterns, bending around Earth's core or skirting massive slabs of rock. Like a flashlight beam hitting a wall, the waves couldn't penetrate certain structures, leaving behind dark patches in the data. But instead of treating these gaps as missing information, scientists turned them into a roadmap. By studying where the waves vanished, they could reverse engineer the shape and composition of the layers below. It's a bit like listening to an echo in a canyon. The silence tells you just as much as the sound. One of the most dramatic revelations came when seismic shadows exposed the boundary between Earth's molten outer core and its solid mantle. Waves passing through the core would suddenly slow down or change direction, creating a shadow zone on the opposite side of the planet. This discovery didn't just confirm the existence of Earth's core, it revealed its texture, density, and even how it moves over time. And the surprises didn't stop there. Shadows have since uncovered sunken tectonic plates, remnants of ancient oceans swallowed by subduction zones, and even pockets of water trapped hundreds of miles underground. What makes this science so powerful is its simplicity. Unlike drilling miles into the crust or sending probes to the mantle, seismic shadows let researchers scan the planet without ever breaking ground. Every earthquake, whether a faint tremor or a catastrophic rupture, sends out waves that illuminate the darkness. And with each new shadow mapped, we're piecing together a story written in stone, one that stretches back billions of years. So the next time you feel the ground shake, remember, those vibrations aren't just a momentary disturbance. They're part of an endless conversation between Earth and those who know how to listen. It all started with a simple mystery. Why did some earthquakes leave behind silent patches in the data? In the early 1900s, scientists scratching their heads over earthquake records stumbled onto something extraordinary. Richard Dixon Oldham, a British geologist studying the massive San Francisco earthquake of 1906, noticed something peculiar. Seismic waves from distant quakes weren't just weaker in certain places, they vanished entirely. At first, many dismissed these gaps as equipment failures or anomalies, but Oldham saw them for what they were, evidence of something massive and unseen deep within our planet. His eureka, a moment came when he realized these silent zones weren't random. They formed a distinct pattern, almost like a shadow cast by an invisible object. And that object, he theorized, was Earth's core. The waves hitting this dense, molten boundary bent sharply or stopped altogether, leaving behind those telltale gaps. It was as if the planet itself was hiding its deepest layer until seismic shadows gave it away. Oldham's discovery didn't just rewrite geology textbooks, it opened an entirely new way of seeing Earth. Instead of relying on drills or surface observations, scientists could now use the absence of sound to map the unseen, but the story didn't end there. As seismographs became more sophisticated, researchers began spotting even subtler shadows, ones that revealed not just the core's existence, but its intricate structure. In the 1930s, Danish seismologist Inge Lehmann made another leap forward. She noticed faint echoes within the shadow zones, hints that the core wasn't just a molten blob but had a solid inner heart. These discoveries weren't just academic curiosities. They helped explain why compass needles point north, how continents drift, and even why some earthquakes unleash far more destruction than others. What's remarkable is how these early pioneers turned gaps in data into a revolutionary tool. They didn't have supercomputers or satellite imaging, just paper records, patience, and a willingness to listen to the silence. And that's the beauty of seismic shadows. They remind us that sometimes the most profound truths aren't found in what we can see or hear, but in the empty spaces between. Today, their legacy lives on every time a new tremor helps us uncover lost tectonic plates, ancient magma chambers, or even clues about other planets. Because if Earth's core taught us anything, it's that the quietest whispers often carry the loudest truths. To understand how seismic waves reveal Earth's hidden layers, let's break down how they actually move through our planet. Picture throwing a stone into a still pond. The ripples spread outward in all directions. Earthquakes work similarly, sending energy pulsing through the ground in distinct patterns. The fastest waves, called P waves, are the first to arrive at monitoring stations. These compressional waves can push through anything: solid rock, molten magma, even water, like a slinky stretching and compressing as it moves. Then come the S waves, slower but more destructive, shaking the ground side to side like a rope being whipped. Here's the catch: while P waves can travel through Earth's liquid outer core, S waves hit an invisible wall. That difference becomes our first clue about what lies beneath. When these waves encounter boundaries between materials, say, where the rocky mantle meets the liquid core, they don't just stop. They bend, bounce, or change speed dramatically. It's like shining a flashlight through a prism. The light doesn't disappear, it splits into new directions. Seismologists use global networks of sensors to catch these altered waves, building a detailed map from thousands of tiny distortions. Some waves take unexpected detours, arriving late after skirting dense rock formations. Others vanish entirely, creating those telltale shadow zones that first revealed Earth's core. The real magic happens when scientists combine data from quakes worldwide. A tremor in Japan might send waves slicing through the Pacific, while an earthquake in Chile illuminates a completely different cross-section. Over time, these overlapping snapshots merge into a three-dimensional portrait of our planet's interior. Recent advances have uncovered astonishing details: vast reservoirs of water trapped in mantle rock, sunken tectonic plates fossilized deep below continents, even towering plumes of superheated rock rising from the core. Perhaps most remarkably, this technique isn't limited to Earth. When NASA in Zealandia placed a seismometer on Mars, it detected quakes with shadow patterns hinting at a surprisingly large liquid core. Back home, seismic imaging has practical applications too, helping locate oil reserves, assess earthquake risks, and even monitor nuclear tests. Every tremor, whether natural or human-made, adds another brushstroke to our growing masterpiece of the subterranean world. What started as a simple observation that some earthquake waves go missing has blossomed into one of science's most powerful diagnostic tools. By listening carefully to how the planet rings like a bell after each quake, researchers continue decoding messages written in stone, magma, and molten metal. And with each passing year, our maps grow sharper, revealing landscapes more alien and wondrous than anything on the surface. Beneath the waves and sediment lies a lost world we're only beginning to map, not through diving suits or submarines, but by decoding the way earthquake waves ricochet through these forgotten landscapes. Take Zealandia, for instance. This sprawling underwater continent, nearly twice the size of India, remained hidden until seismic shadows exposed its contours. The waves revealed something astonishing. Not just random seafloor, but the clearest evidence of a landmass that once connected Australia and Antarctica over 80 million years ago. As the waves slowed over Zealandia's thick granite crust identical to continental rock, they painted a picture of ancient forests, river valleys, and mountain ranges now drowned beneath the Pacific. But submerged continents are just the beginning. Seismic data has uncovered even stranger relics, like a 2,000-mile-long ribbon of mountains entombed beneath the Amazon rainforest. These peaks, taller than the Alps when they formed 300 million years ago, now lie buried under miles of sediment. Yet when earthquake waves hit this hidden range, they bounce back with a signature only solid rock can produce. It's as if the planet preserved a fossil of its own skeleton, waiting for us to notice. The real surprise: some of these lost landscapes aren't ancient at all. Off the coast of Norway, fishermen long whispered about odd currents and shallow spots where no charts showed land. Then seismologists found the cause: an entire glacial valley carved during the last ice age, now submerged but still redirecting ocean currents like an invisible hand. Even more recently, surveys in the North Sea revealed a sprawling prehistoric river system nicknamed Doggerland, where mammoths once roamed and early humans built settlements before rising seas swallowed it 8,000 years ago. What makes these discoveries so groundbreaking is how they rewrite human history alongside geological timelines. In Turkey, seismic anomalies led archaeologists to a buried Bronze Age city near the famous Hittite capital of Hattusa. The vibrations detected not just walls, but the hollow spaces of collapsed tunnels and storage chambers, ghostly echoes of daily life frozen underground. Similarly, in the Sahara, missing seismic waves exposed the path of an ancient river that may have guided early migrations out of Africa, its course now marked by nothing but subtle vibrations in the sand. Every time scientists analyze these shadows, they're essentially time traveling. The waves don't just show us where things are, they reveal how landscapes lived, shifted, and died across epochs. A single seismic profile might capture the birth of a mountain range, the slow creep of tectonic divorce that split continents, or the sudden flood that erased a civilization. And with each discovery, we're reminded that the ground beneath us is never as still as it seems. It's a living archive, pulsing with stories only earthquakes can tell. Deep inside our planet, hidden beneath thousands of miles of rock and molten metal, spins a mystery that took centuries to uncover: Earth's inner core. For decades after scientists first detected the outer core, they assumed it was entirely liquid, a churning sea of iron and nickel. But in 1936, Danish seismologist Inge Lehmann noticed something peculiar. P waves from distant earthquakes weren't just bending around the core, some were ricocheting off an unseen boundary deep within it, like echoes bouncing off a hidden wall. These faint reflections, buried in seismic data that others had overlooked, revealed an astonishing truth. At the heart of our planet lies a solid metal sphere, nearly as hot as the sun's surface, yet locked under unimaginable pressure. This discovery didn't just add another layer to Earth's structure, it rewrote the rules of planetary science. The inner core, roughly the size of Pluto, spins independently from the rest of the planet, creating a cosmic dynamo that generates Earth's magnetic field. Without this invisible shield, solar winds would strip away our atmosphere, turning the planet into a barren wasteland. But here's where it gets even stranger. The core doesn't rotate at the same speed as the mantle or crust. It's racing ahead, completing an extra turn roughly every 1,000 years, like a hidden engine driving the planet's magnetic heartbeat. What makes this even more fascinating is how much we still don't know. Recent studies suggest the inner core might have its own landscape, mountains and valleys sculpted not by wind or water, but by the slow crystallization of molten metal as it cools. Some researchers even speculate about a mysterious innermost core, a distinct layer with properties that defy current models. And then there's the enigma of time. Because seismic waves take minutes to traverse the planet, the shadows they cast are snapshots of the past. When we detect a wave bending through the core today, we're seeing how it looked decades or even centuries ago, depending on the depth. It's like reading a letter mailed from Earth's center, written in the language of vibrations. The implications stretch far beyond geology. Understanding the core's behavior could help predict magnetic pole shifts, which have flipped hundreds of times in Earth's history with catastrophic consequences for life. It might explain why some planets, like Mars, lost their protective magnetic fields while others, like Jupiter, maintain fierce ones. And for those dreaming of future technologies, the core's extreme conditions where iron behaves like a bizarre hybrid of solid and liquid could unlock new materials or energy sources we can't yet imagine. Every earthquake sends fresh whispers from this hidden realm, offering clues we're only beginning to decipher. The shadows that once seemed like gaps in our knowledge have become windows into Earth's deepest secrets. And as instruments grow more sensitive, who knows what else we'll discover? Perhaps the core holds records of ancient asteroid impacts, traces of Earth's formation, or even clues about the fate of other worlds. One thing's certain, the story of our planet isn't written just on its surface, but in the silent pulses of a spinning metal heart we've only just learned to hear. Some of the most dramatic chapters in Earth's history weren't written in stone, they were carved into the planet's very structure, leaving marks that only seismic shadows can reveal. Take the infamous Chixilub crater, the 100-mile-wide scar buried beneath Mexico's Yucatan Peninsula. For decades, this ground zero of the dinosaur extinction was just a theory, until geophysicists noticed something odd in seismic surveys. Waves traveling through the region didn't behave as they should. Some bounced back prematurely, others curved strangely, all pointing to a colossal impact structure hidden under layers of limestone. The telltale shadow pattern revealed a crater so massive it altered global climate in an instant, proving how a single extraterrestrial collision could rewrite life's trajectory. But asteroid strikes aren't the only catastrophes etched into Earth's seismic record. Beneath the picturesque geysers of Yellowstone National Park lies a different kind of time bomb, a supervolcano whose past eruptions dwarf anything in human history. When researchers analyzed seismic waves passing through the area, they encountered mysterious zones where vibrations slowed to a crawl. These anomalies trace the outline of gargantuan magma chambers, some large enough to swallow entire mountain ranges. The shadows tell a chilling story. 3 apocalyptic eruptions over the last 2 million years, each thousands of times more powerful than Mount St. Helens. And the same waves hint at restless movement beneath the surface today, helping scientists gauge whether, or when, this sleeping giant might wake again. What makes these discoveries so vital isn't just their scale, but their lessons. The seismic fingerprints of ancient disasters serve as blueprints for understanding modern threats. When researchers studied the 2004 Indian Ocean tsunami, they found its waves had eerily similar patterns to prehistoric mega-tsunamis preserved in coastal sediment layers. Likewise, the slow creep of tectonic plates today mirrors movements that triggered devastating quakes centuries ago. By comparing fresh seismic data with these ancient shadows, we're essentially running disaster drills across geological time, identifying which fault lines are overdue for rupture, or which volcanic systems show troubling parallels to their explosive past. Perhaps most remarkably, this technique isn't limited to Earth. When NASA Mars rovers detected seismic activity on the red planet, the wave patterns revealed impact craters and extinct volcanoes with striking similarities to features in our own seismic shadow archives. These interplanetary echoes suggest that catastrophe and recovery are universal processes written in the vibrational language of planets. Back home, the same principles help engineers design earthquake-resistant skyscrapers or assess nuclear test sites, proving how Earth's darkest hours can illuminate our path forward. Every time a seismograph picks up those subtle vibrations, it's not just measuring the present, it's eavesdropping on a conversation between past and future, where yesterday's disasters whisper warnings about tomorrow. Not every earthquake announces itself with violent tremors or crumbling buildings. Some unfold in near-total silence, releasing energy so gradually that it takes weeks, sometimes months, for the ground to shift, all without a single noticeable shake. These are slow slip events, often called silent earthquakes, and they're rewriting our understanding of how tectonic plates move. Unlike their dramatic counterparts, these stealthy shifts don't trigger seismic alarms or send people running into the streets. Instead, they creep along fault lines like invisible hands pushing continents apart, leaving behind only faint traces in the data. But here's the catch. These quiet events might hold the key to predicting some of Earth's most devastating disasters. Take the Cascadia subduction zone off the Pacific Northwest coast, where the ocean floor is sliding beneath North America at a glacial pace. Every 14 months or so, GPS sensors detect something peculiar, the land suddenly lurching westward by several centimeters, then stopping just as mysteriously. These silent slips last for weeks, releasing energy equivalent to a magnitude 7 earthquake, yet no one feels a thing. The real revelation came when scientists noticed a pattern. These events often cluster in the decades leading up to catastrophic megathrust quakes, like the one in 1700 that sent a tsunami crashing into Japan. It's as if the fault is whispering warnings before it screams. What makes silent earthquakes so tricky to study is their subtlety. Traditional seismometers miss them entirely, so researchers rely on a clever workaround tracking the shadows they cast. As stress builds along a fault, it subtly alters how seismic waves travel through the rock. Waves passing through a zone primed for a silent quake might slow down or change frequency, creating a telltale fingerprint in the data. In Japan, where slow slip events are monitored with millimeter precision, these shadows have helped forecast volcanic eruptions, with silent quakes often preceding magma movement by days or weeks. The implications are staggering. If we can decode these quiet signals, we might one day predict major quakes with enough lead time to save lives. Already, silent earthquakes have exposed hidden sections of faults previously thought inactive, like the discovery of creeping movements beneath Mexico City, a metropolis built on an ancient lakebed that amplifies seismic waves. Other research suggests these events could even act as pressure valves, releasing strain in harmless increments that prevent larger, deadlier ruptures. But the story doesn't end there. Silent quakes have been spotted in unlikely places, from the icy flanks of Alaska's glaciers to the depths of New Zealand's alpine fault. Some scientists speculate they might explain mysterious seafloor booms heard by submarines, or even strange animal behavior before disasters. One thing's certain: in Earth's seismic symphony, the quietest notes might carry the most urgent messages. And as our instruments grow sharper, we're learning to listen. The journey from tracking earthquakes with simple swinging pendulums to decoding them with artificial intelligence reads like a sci-fi novel. In the late 19th century, the first seismographs were little more than weighted pens dangling over smoked paper, recording every tremor with shaky, handwritten lines. Fast forward to today, and that same basic principle has exploded into a digital revolution. Now, supercomputers crunch seismic data in real time, spotting patterns so subtle they'd slip past even the most trained human eye. Take those faint echoes from mantle plumes, vast upwellings of superheated rock that rise from near the core. For decades, they were little more than theoretical ghosts in the data. But modern AI algorithms trained on millions of past quakes can isolate those whispers from the noise, turning conjecture into vivid 3D maps of Earth's hidden furnace. Yet AI isn't working alone. Overhead, satellites armed with radar so precise they can detect ground movements as slight as a millimeter add another layer to the story. This technology, called InSAR, works like a celestial measuring tape, scanning the same patch of Earth over and over. When paired with seismic data, it reveals how land bulges before volcanic eruptions or how cities slowly sink due to groundwater extraction. In Turkey, InSAR spotted ominous uplift along the North Anatolian Fault years before the devastating 2023 quakes, a silent warning written in the language of shifting pixels. What makes this technological synergy so groundbreaking is how it fills in the gaps. Seismic shadows might hint at a buried fault, but InSAR shows it creeping. AI can predict how waves might bounce through a newly discovered magma chamber, while satellite data confirms whether that chamber is inflating with fresh molten rock. Together, they're rewriting the rules of exploration. Off the coast of Antarctica, this combo uncovered a hidden network of subglacial lakes, not by drilling through miles of ice, but by analyzing how seismic waves slowed as they passed through liquid water trapped below. The implications stretch far beyond pure science. In California, machine learning models digest live seismic feeds to issue early warning seconds before shaking hits urban areas, enough time for trains to brake or surgeons to pause operations. In Iceland, AI-driven forecasts help geothermal plants avoid triggering quakes while tapping Earth's heat. Even archaeologists have joined the revolution, using ground-penetrating radar and seismic tomography to locate buried pyramids or lost Viking ships without lifting a shovel. Perhaps most astonishing is how quickly these tools are evolving. Early seismographs took days to process a single quake. Now, neural networks analyze thousands simultaneously, spotting precursor tremors that might hint at bigger quakes to come. And with quantum computing on the horizon, we could soon simulate entire fault systems atom by atom. Yet for all their power, these technologies share one humble goal: to listen more clearly than ever to the stories Earth tells in the spaces between the shakes. Because every shadow, every echo, every millimeter of movement is another piece of a puzzle 4.5 billion years in the making. The story of Helike reads like an ancient Greek tragedy, a thriving city, home to philosophers and merchants, erased in a single cataclysmic night. According to historical accounts, in the winter of 373 BC, Helike's citizens reported strange portents: animals fleeing inland, springs running dry, and eerie lights flickering over the sea. Then, without warning, the ground convulsed. Buildings crumbled as the sea surged inward, dragging the entire city beneath the waves. By morning, Helike was gone, leaving only a few survivors to whisper its legend. For over 2,000 years, scholars debated its exact location, treating it as a myth until seismic shadows pulled it back from obscurity. In the 1980s, a team of archaeologists and geologists noticed something unusual in seismic surveys of the Gulf of Corinth. The waves behaved oddly near the coastline, bending and scattering as if hitting buried obstacles. Traditional sonar had missed these anomalies, but the subtle distortions in the seismic data painted a different picture. Beneath layers of sediment lay the ghostly outline of structures, walls, roads, even the faint grid of a city plan. When divers finally excavated the site, they found pottery, coins, and stone columns, all preserved in a watery tomb. The seismic shadows hadn't just located Helike, they'd captured the moment of its destruction, frozen in time. What made this discovery groundbreaking wasn't just solving an ancient mystery, it was how it reshaped two fields at once. For geologists, Helike became a textbook example of seismic liquefaction, where solid ground turns to quicks, and during an earthquake, the same surveys revealed a hidden fault line, proving the region was far more volatile than previously thought. For archaeologists, the find offered a rare snapshot of a classical city in its final hours, untouched by later civilizations. Even the positioning of artifacts told a story. Collapsed roofs facing the same direction hinted at the tsunami's deadly path, while crushed pottery marked where shelves had toppled in the quake. But perhaps the most startling revelation was how modern technology validated ancient accounts. Greek historians like Strabo had described Helike's destruction in vivid detail, but their records were long dismissed as exaggerated folklore. The seismic data didn't just confirm their accuracy, it added new layers. Sediment cores showed traces of saltwater inundation matching the tsunami's timeline, while shifted tectonic plates explained why the city sank rather than simply crumbling. Even the eerie lights mentioned in texts found an explanation. Scientists now theorize they were earthquake lights, a rare phenomenon where electrical charges illuminate the sky during seismic activity. Helike's legacy extends far beyond archaeology. Today, its rediscovery serves as a blueprint for finding other lost cities, from sunken ports along the Nile to Mayan settlements buried under volcanic ash. The same techniques have even pinpointed shipwrecks in the Baltic, where seismic waves bounce off preserved wooden hulls. And for coastal communities, Helike's fate is a chilling reminder. The ground beneath our feet holds memories of disasters past, and sometimes those memories echo loudest in the silence between the waves. The next time you walk along a shoreline, remember, the Earth isn't just keeping its secrets, it's waiting for the right tools, the right questions to reveal them. Beneath Antarctica's frozen expanse lies a world as alien as any distant planet, sculpted not by wind or water, but by the crushing weight of ice 2 miles thick. Seismic waves sent pulsing through this icy desert have uncovered a hidden realm of jagged mountain ranges, deep valleys, and even rivers that flow in perpetual darkness. But the most startling revelations came when those waves hit something unexpected: vast, liquid lakes trapped between bedrock and ice, untouched by sunlight or air for millions of years. Lake Vostok, the largest of these subglacial wonders, is a time capsule sealed under 13,000 feet of ice. When seismologists first detected its flat, mirror-like surface in the 1990s, it defied all logic. How could liquid water exist in one of Earth's coldest places? The answer lies in the ice itself, a colossal insulating blanket combined with geothermal heat rising from below. But the real mystery isn't just how the lake survives, but what might live there. Seismic shadows hint at an ecosystem isolated for 15 million years, where microbes could thrive in conditions resembling Jupiter's icy moon Europa. When Russian scientists finally drilled into Vostok in 2012, they found genetic traces of extremophiles organisms that rewrite the rules of where life can exist. These discoveries aren't just scientific curiosities, they're urgent clues about our planet's future. As seismic data maps the contours beneath Antarctica's ice, it reveals something startling. The ice sheet isn't a static monolith, but a dynamic system with hidden weak points. In some areas, lubricating water from subglacial lakes speeds glaciers toward the sea like slipping on a wet floor. Elsewhere, ancient river channels funnel warm ocean water inland, melting ice from below. Each seismic profile adds another piece to the puzzle of how ice responds to warming and how quickly seas might rise. The stakes couldn't be higher. West Antarctica's Thwaites Glacier, nicknamed the Doomsday Glacier, has already doubled its flow speed since the 1990s. Seismic surveys show why: a network of hidden cavities where warm water erodes its underbelly. If Thwaites collapses, it could trigger a chain reaction, lifting global sea levels by 10 feet or more. But here's where the shadows offer a glimmer of hope. By pinpointing these vulnerabilities, scientists can predict which glaciers are most at risk and which might stabilize if we act in time. What makes this research so revolutionary is its dual role as both microscope and crystal ball. The same waves that uncover lost landscapes also simulate how ice will behave as temperatures climb. And as drones and AI join traditional seismographs, we're gaining an unprecedented view of this frozen frontier. Every tremor, every echo, every shadow is a message from a world we're only beginning to understand. One that holds the keys to our past and perhaps our survival. Volcanic eruptions don't just explode out of nowhere. They brew in hidden chambers deep beneath the surface, where magma creeps through a labyrinth of tunnels like water through plumbing. But here's the twist: we can't see these molten highways directly. Instead, scientists rely on seismic shadows to map them, using earthquake waves as their flashlight. When vibrations pass through a volcano, they slow down near magma-filled cavities or speed up through solid rock, leaving behind a trail of clues. It's like tapping on a wall to find a stud, except the wall is a mountain, and the stud could unleash a catastrophe. Take Mount St. Helens in 1980. Weeks before its infamous eruption, seismometers picked up something unusual. Tiny quakes kept clustering in the same spot, but the waves they produced had odd gaps, shadows that pointed to a growing magma chamber just north of the summit. As pressure built, the ground itself began to bulge, rising nearly 5 feet a day. Scientists had never seen such clear warning signs before. When the mountain finally blew on May 18th, the eruption followed the exact path those seismic shadows had outlined. The disaster was devastating, but it could have been far worse without that heads-up. Today, similar shadows help monitor active volcanoes worldwide, from Iceland's fiery Fagradalsfjall to the simmering giant beneath Yellowstone. What makes this science so powerful is its precision. By analyzing how waves bend around magma conduits, researchers can estimate not just where molten rock is pooling, but how fast it's moving. In Italy's Campi Flegrei, a supervolcano near Naples, seismic shadows recently revealed magma rising at an alarming rate, data that prompted officials to update evacuation plans. In Hawaii, shadows traced the underground river of lava that fed Kilauea's 2018 eruption, allowing communities to anticipate which neighborhoods were in the danger zone. But the real breakthrough lies in prediction. Magma doesn't move randomly, it follows paths of least resistance, often reusing old channels from past eruptions. By comparing seismic shadows across decades, scientists can spot patterns, like how certain volcanoes tend to give weeks of subtle warnings before erupting, while others blow with little notice. In Iceland, this approach helped forecast the 2010 Eyjafjallajökull eruption early enough to reroute flights across Europe. In Indonesia, shadow patterns under Mount Merapi now trigger alerts that give villages precious hours to evacuate. The stakes are especially high in places like Mexico City, built atop the ancient lakebed of Lake Texcoco. When seismic waves pass beneath nearby Popocatépetl, they slow dramatically, a sign of massive magma reservoirs just 20 miles from 20 million people. But here's the hopeful part. Every shadow mapped is another piece of the puzzle, another chance to outsmart nature's fury. From thermal cameras tracking ground temperature to AI algorithms analyzing quake swarms, technology is turning these invisible clues into lifelines. And as our maps of the underworld grow clearer, so does our ability to listen when the Earth starts whispering its warnings. Down where sunlight never reaches and pressures could crush a submarine, life isn't just surviving, it's thriving in ways that defy everything we thought possible. Scientists call it the deep biosphere, a hidden realm of microorganisms living miles beneath our feet, tucked into microscopic cracks and pores within Earth's crust. These aren't your average bacteria. They're extremophiles, life forms that flourish in conditions that would be lethal to nearly every other organism on the planet, scorching temperatures, crushing pressures, and environments devoid of oxygen or organic food. And the only reason we know they exist, seismic shadows. When researchers first noticed strange slowdowns in seismic waves passing through certain rock layers, they assumed it was due to water or gas pockets. But drilling projects like South Africa's Mponeng gold mine revealed something far more astonishing. At depths where temperatures exceed 140 degrees Fahrenheit, seismic anomalies led scientists to colonies of Candidatus disulfurudis audaxviator, a bacterium that lives entirely independent of the sun. It survives by feeding on radioactive minerals, breaking down rocks for energy, and recycling its own waste in a self-sustaining loop. This single species rewrote biology textbooks, proving life could persist without photosynthesis or even oxygen, a revelation that echoes far beyond our planet. The implications for astrobiology are staggering. If Earth's crust harbors life in such extreme conditions, why couldn't Mars or Europa? NASA's Perseverance rover has already detected seismic shadows in Jezero crater that mirror patterns linked to underground water and potentially microbial habitats on Earth. Meanwhile, Europa Clipper's upcoming mission will use ice-penetrating radar to hunt for similar anomalies beneath Jupiter's icy moon, where a global ocean may slosh beneath frozen plains. The parallels are impossible to ignore. Just as seismic waves exposed Earth's deep biosphere, they might soon reveal extraterrestrial ecosystems hiding in plain sight. What makes these shadow-dwelling microbes so revolutionary isn't just where they live, but how they've adapted. Some species form biofilms that alter the very rock around them, secreting minerals that change how seismic waves travel. Others cluster around hydrothermal vents, creating living networks that span entire fault lines. In Sweden's Esper Hard Rock Laboratory, scientists found bacteria thriving in granite fractures so tiny they're invisible to the naked eye, yet their collective metabolism leaves a detectable imprint on seismic surveys. It's as if the planet itself is breathing, with each microbial community adding its own rhythm to Earth's vibrations. The hunt for these hidden ecosystems has turned geology into a detective story. In Oman's Samail ophiolite, where Earth's mantle rocks are exposed at the surface, seismic anomalies led to the discovery of microbes eating methane and hydrogen gases that could fuel life on Saturn's moon Enceladus. In the oceanic crust beneath the Atlantic, shadow patterns revealed vast bacterial mats coating underwater volcanoes, surviving on chemical reactions between seawater and molten rock. Each find stretches our understanding of where life can exist, both on Earth and beyond. Perhaps the most profound lesson lies in resilience. These microbes have endured mass extinctions, ice ages, and continental shifts by retreating into the planet's cracks, a survival strategy that might be universal. If life can cling to existence in Earth's most inhospitable corners, then the shadows flickering through Martian seismograms or the icy shells of distant moons might not be so silent after all. They could be whispers from a hidden biosphere waiting for us to listen. Even on its calmest days, our planet never truly rests. Beneath the quiet surface, Earth pulses with a mysterious low-frequency vibration, a deep, steady hum that resonates through the crust like the lowest note on a piano, sustained endlessly. This isn't the rumble of earthquakes or the groan of shifting tectonic plates. It's something far subtler, a whisper of energy so faint that for decades, scientists debated whether it even existed. Then, in the late 1990s, seismic shadows revealed the truth. The hum is real, and it's singing the story of our planet's hidden rhythms. The source of this otherworldly sound might surprise you. It begins with ocean waves, not the gentle lapping at shorelines, but the colossal energy of storms thousands of miles out at sea. When these waves collide with continental shelves, they don't just break and retreat. Their energy transfers into the seafloor, sending pulses rippling through the Earth's crust like fingertips dragging across a drumhead. These vibrations travel at frequencies too low for human ears to detect, between 2 and 7 millihertz, a range so deep it's closer to a feeling than a sound. But sensitive seismographs can pick them up, revealing a pattern so consistent it's been dubbed Earth's heartbeat. What makes the hum so fascinating isn't just its existence, but what it tells us about how our planet functions. Unlike earthquakes which strike unpredictably, the hum is a constant background signal, a baseline against which other seismic activity can be measured. By studying how these vibrations bend and scatter, creating shadows as they interact with different layers, scientists have mapped previously invisible features, like ancient magma chambers or hidden water reservoirs. In Japan, researchers even used the hum to detect stress building along fault lines months before major quakes, turning this ambient noise into an early warning system. But the revelations don't stop there. The hum's behavior changes with the seasons, growing stronger in northern winters when Atlantic storms rage most fiercely. It fluctuates with climate patterns like El Niño, offering a new way to track how ocean energy shifts across the globe. And perhaps most astonishingly, it might hold clues about Earth's core. Some theories suggest the hum's energy could influence the slow churn of molten metal at the planet's center, potentially affecting the magnetic field that shields us from solar radiation. This phenomenon isn't unique to Earth either. When NASA in Zealandia placed a seismometer on Mars, it detected a similar hum, though weaker and more erratic, suggesting even lifeless planets might vibrate with the memory of ancient impacts or long-dead oceans. Back home, the hum has practical applications too. Oil companies use its signals to probe underground reserves without disruptive drilling, while climate scientists analyze its patterns to study how rising sea levels alter coastal dynamics. The deeper we listen, the more the hum reveals. It's a reminder that our planet is never truly still, that even in moments of apparent calm, energy flows through rock and water in an endless loop. Every crashing wave, every distant storm, every pulse of this silent song is part of a conversation between Earth's surface and its depths, a conversation we're only beginning to understand. And as our instruments grow more sensitive, who knows what other secrets we'll uncover in the spaces between the notes. Deep within the rock layers of the Appalachian Mountains lies a forgotten earthquake, not recorded in human history, but etched permanently into stone. 300 million years ago, when these peaks were young and the landmasses we know today were still colliding, a massive tremor rippled through the crust. The force was so immense it didn't just shake the ground, it folded solid rock like taffy, leaving behind permanent wrinkles in the Earth's skin. Today, geologists call these distortions fossilized seismic waves, and they're some of the most vivid time capsules of our planet's violent past. What makes these ancient scars so valuable is how they mirror modern seismic shadows. When researchers compare the warped rock layers in the Appalachians to the way earthquake waves behave today, they're essentially reading the same story in two different languages. The folds and fractures tell us not just how hard the quake hit, but its direction, depth, and even how long it lasted. In some spots, the rock shows textbook examples of liquefaction, where solid ground briefly turned to quicks, and identical to effects seen in contemporary quakes like the 1989 Loma Prieta event. Other formations reveal fault gouge, a pulverized rock paste created when two slabs grind against each other, leaving a permanent record of the friction that once shook the land. One of the most startling discoveries came from Central Virginia, where a peculiar zigzag pattern in the bedrock puzzled geologists for decades. Then, in 2011, a magnitude 5.8 earthquake struck nearby, and suddenly the ancient clues made sense. The modern quake's seismic shadows matched the fossilized waves perfectly, proving the same fault had ruptured repeatedly over eons. This wasn't just academic detective work. It revealed a seismic threat no one knew existed, hidden in plain sight for millions of years. But fossilized waves aren't limited to dry land. Off the coast of Japan, underwater scans have uncovered similar distortions in sediment layers dating back to the year 869, evidence of a tsunami so powerful it dwarfed even the 2011 Tohoku disaster. By pairing these ancient underwater scars with modern sonar shadow data, scientists reconstructed the entire event, from the initial seafloor rupture to the waves' devastating inland surge. The chilling conclusion: these mega tsunamis strike the region roughly every 1,000 years, meaning another could be due any century now. Perhaps most remarkably, these time-warped vibrations are helping rewrite the rules of plate tectonics. In the Rocky Mountains, fossilized waves show that some quakes didn't follow known fault lines at all. They ripped through supposedly stable continental interiors, a phenomenon once thought impossible. Similar surprises in Australia's outback and Scandinavia's bedrock suggest Earth's crust behaves differently under extreme stress, bending rather than breaking in ways modern seismology is only beginning to understand. Every fold in the rock, every shattered layer, is a message from deep time, a reminder that the ground beneath us has memory. And as we learn to read these petrified tremors alongside their modern shadows, we're not just uncovering Earth's past. We're preparing for its future. Beneath the familiar blue expanse of Earth's oceans lies another, far vaster sea, one hidden not under waves, but locked within the very rock of the planet itself. Seismic waves pulsing through the mantle have uncovered something astonishing. Colossal reservoirs of water trapped inside minerals, bound so tightly that a single cubic foot of rock might hold gallons of liquid. This isn't water as we know it, not lakes or rivers, but molecules woven into the crystal structure of minerals like ringwoodite, a gem-like form of olivine that forms under extreme pressures hundreds of miles down. The numbers defy imagination. Scientists estimate this subterranean ocean could hold 3 times the volume of all the water on Earth's surface combined, cycling slowly over geological timescales in a process that redefines what we thought we knew about the planet's water cycle. The discovery began with a paradox. For decades, geologists struggled to explain why some seismic waves slowed dramatically when passing through certain zones of the mantle, as if hitting pockets of molten rock. But the temperatures at those depths didn't match magma formation. Then, in 2014, experiments with ringwoodite solved the riddle. When subjected to mantle-like pressures, the mineral absorbed water like a sponge, altering its structure just enough to bend seismic waves in ways that perfectly matched the mysterious shadow zones. Suddenly, those anomalies weren't gaps in the data, they were signposts pointing to an entire hidden hydrosphere. What makes this underground ocean so revolutionary is how it challenges the origins of Earth's water. The traditional theory held that our oceans were delivered by icy comets during the planet's violent infancy. But if vast quantities of water existed deep in the mantle all along, it suggests Earth was born wet, its water baked into the fabric of the planet from the start. This would explain why Venus and Mars, formed from similar materials, show traces of ancient water despite their barren surfaces today. Our world's oceans might not be borrowed. They could be homegrown, sweating up from below over billions of years through volcanic cracks and mid-ocean ridges. The implications ripple far beyond geology. This slow-motion water cycle could be the missing link in understanding everything from continental drift to the emergence of life. Water trapped in mantle minerals lowers the melting point of rock, making it easier for tectonic plates to slide, a subtle lubricant that keeps Earth's engine running. Some researchers even speculate that these deep reservoirs might act as stabilizers, buffering surface oceans against extreme climate shifts over eons. And if life can thrive in the crushing depths of the Mariana Trench, who's to say it couldn't exist in the high-pressure chemistry of these hidden water-bearing rocks? Yet for all we've learned, the full picture remains tantalizingly out of reach. Recent seismic surveys hint at even deeper water storage, perhaps near the core mantle boundary where minerals like Dave meet a hoard oceans worth of water in their crystalline cages. Others suggest these reservoirs might occasionally bleed upward in colossal eruptions, flooding the surface in cataclysmic events that could explain mysterious sea level spikes in the fossil record. One thing's certain, the old image of Earth's water cycle evaporation, rain, rivers returning to the sea, is just the surface ripple of a story that stretches thousands of miles down. Every earthquake, every tremor sends new whispers through this labyrinth of hidden seas, and we're only beginning to learn their language. When the Apollo astronauts placed seismometers on the moon's surface in the late 1960s and early 70s, they expected to record the occasional meteorite impact, not an entire hidden world of lunar tremors. Yet the data that trickled back to Earth revealed something extraordinary. The moon, that silent companion in our night sky, was alive with vibrations. These weren't just random shudders. They followed patterns, clustering in specific regions and depths, painting a picture of a celestial body far more dynamic than anyone had imagined. The most surprising discovery: some of these moonquakes originated deep below the surface, in zones where seismic shadows hinted at a partially molten core, much like Earth's. The implications were staggering. For centuries, scientists had assumed the moon was a cold, geologically dead rock, but the Apollo seismometers told a different story. Just like our planet, the moon had layers: a crust, a mantle, and likely a core with pockets of molten material. The shadows in the data revealed how seismic waves slowed and bent as they passed through these layers, creating gaps that mirrored the behavior of waves traveling through Earth's interior. One particular type of moonquake, dubbed deep moonquakes, occurred roughly 700 kilometers below the surface, near the boundary where a semi-solid mantle might meet a liquid outer core. These weren't random events. They happened in sync with the moon's orbit, triggered by Earth's gravitational pull stretching and squeezing its interior like a tidal force. But the moon's seismic activity wasn't limited to deep tremors. The Apollo instruments also picked up shallow moonquakes, some powerful enough to last over 10 minutes, far longer than most earthquakes. These vibrations didn't fit the usual patterns of tectonic activity, leaving scientists puzzled. Then came the most unsettling discovery of all. Some of these quakes seemed to originate near the edges of massive, buried formations called mascones, dense regions of concentrated mass that subtly distort the moon's gravity. Were these quakes caused by ancient lava flows cooling and contracting over billions of years? Or could they be signs of residual tectonic shifts in a world once thought geologically still? The answers aren't just academic. Understanding the moon's inner workings is crucial for the next era of lunar exploration. Future moon bases will need to withstand these tremors, especially if we build near fault lines or unstable regions. Seismic data could even guide us to resources like underground lava tubes perfect for shelter or reservoirs of water ice tucked beneath the crust. And beyond practicality, these discoveries reshape our understanding of how planets form. If the moon, long considered a static relic, still churns with hidden energy, what does that mean for other seemingly dormant worlds? Perhaps the most poetic revelation lies in the moon's echoes of Earth. The same techniques used to map our planet's core, listening for shadows in seismic waves, are now decoding the moon's secrets, proving that even in the vast silence of space, vibrations tell stories. Every moonquake is a whisper from a world we're only beginning to know, a reminder that the universe hums with hidden life, even in places we once thought silent. Predicting earthquakes with pinpoint accuracy remains one of science's greatest challenges, but seismic shadows are revolutionizing how we prepare for the inevitable. These subtle gaps in wave patterns act like X-rays for fault lines, exposing hidden stress points where tectonic plates grind against each other in uneasy truce. Take the San Andreas Fault in California. Seismic surveys have revealed sections where waves slow dramatically, signaling rocks under such strain they're essentially holding their breath. Cities like Los Angeles now use these shadow maps like hazard blueprints, reinforcing bridges and retrofitting buildings precisely where the data shows the highest risk. The power of this approach lies in its precision. Traditional seismic hazard maps relied on historical quake patterns, essentially looking backward to guess future threats. But shadows give us a real-time snapshot of pressure building right now. In Tokyo, where the Pacific Plate dives beneath Japan at a rate of 3 inches per year, scientists track how these stress shadows shift over time. Some subway tunnels have been rebuilt with flexible joints, while skyscrapers incorporate shock-absorbing pendulums, all positioned based on where seismic waves bend most sharply. Yet forecasting isn't just about infrastructure. In Chile, where massive quakes strike every few decades, shadow patterns helped redesign entire neighborhoods. After the 2010 Mall earthquake exposed hidden faults offshore, planners relocated hospitals and emergency centers away from newly identified risk zones. Similar strategies are transforming Istanbul's preparations for the long-overdue Big One along the North Anatolian Fault. By analyzing how waves interact with the seabed beneath the Marmara Sea, engineers are constructing earthquake-resistant schools that double as vertical evacuation sites. The most promising breakthroughs combine shadows with other technologies. Machine learning algorithms now digest centuries of quake data alongside real-time shadow movements, spotting correlations no human could. In New Zealand, this hybrid approach predicted the 2016 Kaikoura earthquake's unusual rupture path months in advance, not the exact day, but the likely direction of destruction. Meanwhile, Japan's earthquake early warning system leverages shadow data to buy precious seconds, stopping trains and shutting off gas lines before shaking even begins. What makes this science so transformative is its humility. Instead of chasing the impossible dream of stopping earthquakes, we're learning to dance with them. From Mexico City's seismic-resistant apartments to Nepal's community warning sirens triggered by wave anomalies, resilience is becoming a shared language. And with each new shadow mapped, we're not just reading the Earth's whispers, we're learning how to answer back. Beneath the golden sands of Egypt, where pharaohs once walked and empires rose and fell, modern technology is uncovering secrets no shovel could ever reach. When researchers scanned the area around the Great Pyramid of Giza with seismic waves, they didn't just see the familiar chambers we've known for centuries, they detected strange voids where the waves scattered or vanished entirely. One particularly tantalizing gap lies just behind the pyramid's north face, a hidden space large enough to be a corridor or even an undiscovered burial chamber. Could this be the lost tomb of a forgotten ruler, or perhaps a repository of ancient knowledge sealed away for millennia? The shadows won't say, but they've set off a hunt that could rewrite history. This isn't just happening in Egypt. Across the globe, seismic surveys are acting like time machines, peeling back layers of soil and stone to reveal civilizations long thought erased. In the jungles of Guatemala, vibrations bouncing off buried limestone led archaeologists to an entire network of Mayan temples and roads, invisible beneath the dense canopy. Off the coast of Greece, subtle distortions in underwater seismic data exposed the skeletal remains of a 2,000-year-old trading ship, its cargo of amphorae still intact on the seafloor. Even in places where history books claimed nothing existed, like the plains of Kazakhstan, these hidden echoes have uncovered sprawling Bronze Age cities that rivaled Mesopotamia in scale. What makes these discoveries so thrilling is how they blend myth and science. For years, locals near Turkey's Mount Ararat spoke of a strange shape beneath the ice, a structure some believed to be the remains of Noah's Ark. When seismologists scanned the area, they found an unnatural, ship-like formation with compartments matching ancient descriptions. Whether it's the biblical ark or a geological oddity, the shadows have turned legend into a tangible mystery. Similarly, beneath Denmark's farmlands, seismic anomalies revealed a massive Viking ring fortress, its circular outline perfectly preserved like a ghostly stamp on the earth. The real magic lies in the details these shadows preserve. In Rome, seismic surveys beneath the Colosseum detected a labyrinth of tunnels and chambers where gladiators and wild animals once waited, their footfalls still faintly etched into the vibrations of the stone. In Peru, hidden passages beneath Machu Picchu showed up as zigzagging shadows, suggesting the Incas built escape routes or secret sanctuaries into their sacred city. And in Cambodia, the same technology mapped an entire lost metropolis around Angkor Wat, proving the temple was just the heart of a sprawling urban jungle swallowed by time. Archaeology is no longer just about digging, it's about listening. Every time a seismic pulse travels through the ground, it carries whispers from builders, warriors, and traders who left no written records. Their stories are written in the gaps, the echoes, the silent spaces where the earth itself remembers what history books forgot. And as our tools grow sharper, who knows what other chapters will recover from the shadows? The weight of ice sheets during an ice age doesn't just sculpt valleys and carve fjords. It presses down on the planet with such force that the very crust beneath our feet bends like a diving board under a swimmer's weight. Then, when temperatures rise and glaciers retreat, the land slowly rebounds, rising like bread dough after the baker's hand lifts away. This dance of compression and release leaves behind a seismic fingerprint, one that scientists are now decoding to understand how Earth's climate and geology have shaped each other over millennia. Take Scandinavia, where the land is still springing back from the last ice age, 12,000 years after the glaciers melted. GPS measurements show parts of Sweden and Finland rising nearly a centimeter per year, a rate that seems negligible until you realize it's the cumulative effect of trillions of tons of vanished ice. Seismic waves passing through this region reveal something extraordinary. The mantle beneath Scandinavia is flowing upward, filling the space once occupied by compressed rock, much like memory foam slowly regains its shape. These subtle movements aren't just geological curiosities. They're time-lapse records of past climate shifts written in stone, but the story doesn't end with ancient ice. Today, as human-driven warming accelerates, scientists are tracking how modern glaciers from Greenland to Patagonia are unloading their weight at unprecedented speeds. In Alaska, where glaciers have lost over 4 trillion tons of ice since the 1990s, seismometers detect a startling phenomenon. The ground is rising so rapidly that it's triggering small earthquakes along once dormant faults. These tremors aren't random. They cluster in zones where seismic shadows indicate the crust is weakest, offering a real-time preview of how Earth's skeleton might adjust to a warmer world. The implications stretch far beyond academic interest. In coastal cities like Vancouver and Oslo, this glacial rebound is tweaking sea level rise calculations. While melting ice pours water into the oceans, the land itself is rising in some regions, offsetting the flood risk for now. But in areas like the Chesapeake Bay, where the crust is still sinking from ice age pressures applied thousands of miles away, the double whammy of subsidence and rising seas spells trouble. Seismic data helps planners pinpoint which neighborhoods will face the steepest challenges decades before the water arrives. Perhaps most crucially, these climate-driven crustal shifts are rewriting the rules of earthquake hazards. In parts of Canada and the northern United States, the slow rebound from long-gone ice sheets is reactivating ancient faults, some silent since the Pleistocene. By comparing seismic shadows from historical quakes with modern stress patterns, researchers have identified regions where the next big tremor might strike not in centuries, but within our lifetimes. It's a stark reminder that the planet's memory is long, and the echoes of climate change reverberate far deeper than the atmosphere. The beauty of this research lies in its duality. Those same seismic waves that unveil Ice Age secrets also help forecast how today's warming will reshape the ground beneath us. From the buckling of Himalayan peaks as glaciers retreat to the subtle inflation of Antarctic bedrock as ice shelves thin, Earth's crust is keeping score. And as we learn to read its language, we're discovering that climate change isn't just a surface story. It's etched into the very bones of the planet. The next frontier in seismic exploration isn't just about seeing deeper. It's about listening more precisely than ever before. Projects like the EarthScope initiative are transforming how we map Earth's hidden layers, blanketing entire continents with dense grids of ultra-sensitive seismometers. Imagine a network so vast it can track a single tremor from California to New York, tracing how its waves twist and bend through every mountain range and sediment basin along the way. These arrays don't just capture earthquakes, they record the planet's constant hum, the subtle creaks of tectonic plates, even the faint echoes of meteorites striking the other side of the globe. The result, a living, breathing 3D model of Earth's interior, updated in real time with resolution so sharp it can pinpoint magma chambers beneath volcanoes or ancient fault lines lying dormant for millennia. But the real game changer might be lurking in the realm of quantum physics. Emerging quantum sensors, no larger than a sugar cube, can detect vibrations so faint they'd slip right past traditional equipment. Where conventional seismometers hear the planet's loudest shouts, these devices catch its whispers, shadows within shadows. Picture this: vibrations from an earthquake that occurred 2,000 years ago, still rippling through the mantle like a fading echo in a cathedral. Or the infinitesimal tremors caused by groundwater shifting deep underground, revealing aquifers we never knew existed. One prototype in Germany even picked up the gravitational tug of passing clouds, a level of sensitivity that could one day let us track storms by how they bend the very crust beneath our feet. What makes these tools so revolutionary isn't just their precision, but their potential to rewrite history. In the deserts of Arabia, ultra-sensitive arrays recently uncovered evidence of a prehistoric megaquake that redirected river systems and reshaped human migration routes. Off the coast of Japan, quantum-enhanced surveys are mapping the submerged ruins of Jomon-era villages with centimeter-scale accuracy, their foundations preserved under layers of volcanic ash. And in the Amazon, where dense foliage hides ancient earthworks, seismic shadows are revealing vast geometric patterns, proof of a lost civilization that thrived where we once saw only wilderness. The implications stretch far beyond archaeology. In the energy sector, these technologies could pinpoint geothermal reservoirs with surgical precision or spot microfractures in oil wells before they become disasters. Urban planners are already using ultra-high-res seismic maps to decide where to build earthquake-resistant skyscrapers or route subway tunnels. Even climate scientists are joining the revolution, tracking how melting permafrost alters the rigidity of Arctic bedrock or how groundwater depletion causes cities to sink. Yet the most exciting discoveries might still lie ahead. Some researchers speculate that next-gen sensors could detect the vibrational fingerprints of dark matter or the remnants of primordial quakes from Earth's formation. Others imagine a global seismic internet, where every smartphone becomes a mini seismometer, crowdsourcing data that predicts quakes before they strike. One thing's certain, as these tools peel back layer after layer of Earth's hidden past, they're not just showing us where we've been, they're lighting the way to where we're going. The shadows are speaking louder than ever. We just needed the right ears to listen. The same seismic shadows that unveil Earth's hidden wonders also force us to confront an uncomfortable question. Just because we can explore these fragile realms, does that mean we should? Take Antarctica's Lake Vostok, sealed under miles of ice for 15 million years. Drilling through that pristine barrier risks contaminating one of the last untouched ecosystems on the planet, a time capsule that could hold clues about life on icy moons like Europa. Yet the lake's waters might also reveal how organisms survive extreme conditions, offering breakthroughs in medicine or biotechnology. It's a paradox as deep as the ice itself. Do we prioritize preservation, or does the potential to save human lives justify the intrusion? This dilemma extends far beyond polar ice. Seismic surveys have pinpointed vast reservoirs of water bound in mantle minerals, lucrative targets for corporations eyeing deep earth mining. The technology exists to tap these subterranean oceans, potentially solving water crises in arid regions. But extracting them could destabilize tectonic plates, triggering earthquakes in unpredictable ways. Similar debates rage over rare earth elements detected beneath protected rainforests or methane hydrates locked under Arctic permafrost. Each discovery pits short-term human needs against long-term planetary health. The legal landscape is just as fractured as the fault lines we study. Antarctica is governed by treaties that suspend territorial claims, but no laws prevent a private company from drilling through its ice if they find a loophole. The high seas, where seismic maps reveal untold mineral wealth, operate under a patchwork of regulations that often prioritize exploitation over conservation. Even national parks aren't immune. Yellowstone's supervolcano magma chambers hold enough lithium to power millions of electric vehicles, but mining them could disrupt geothermal features sacred to indigenous communities and vital to ecosystems. Perhaps the most poignant tension lies between generations. The climate crisis demands urgent solutions, yet some proposed fixes like injecting CO2 into basalt formations mapped by seismic waves carry risks we don't fully understand. Future societies might curse our reckless haste or praise our restraint. Indigenous groups offer alternative frameworks like Bolivia's Law of Mother Earth, granting legal personhood to natural systems, a radical rethinking of ownership that challenges Western notions of resource extraction. As seismic technology peels back Earth's layers with ever sharper clarity, we're not just discovering hidden landscapes, we're navigating an ethical minefield. Every vibration we send into the ground carries two questions. What secrets will it reveal, and what responsibilities will those secrets demand of us? The answers won't be found in the shadows themselves, but in how we choose to illuminate them. Long before scientists began mapping Earth's hidden layers, storytellers were already dreaming of what might lie beneath our feet. Jules Verne's journey to the center of the Earth wasn't just a fantasy, it was a prophecy wrapped in adventure, imagining subterranean oceans and prehistoric worlds illuminated by glowing gases. Verne's 19th century readers might have dismissed his visions as pure fiction, but today, seismic shadows reveal truths just as astonishing. Vast reservoirs of water trapped in mantle minerals, lost continents like Zealandia, and even the faint echoes of dinosaur-killing asteroids preserved in Earth's crust. The line between science and fiction blurs when reality outpaces imagination. Modern sci-fi continues this tradition, using seismic mysteries as springboards for storytelling. In The Core, a film that bends physics to its limits, Earth's inner rotation stutters to a halt, a catastrophe that real-world seismic data actually helps prevent by monitoring the core's subtle movements. Netflix's The Midnight Sky depicts a future where humanity abandons a dying planet, its fate hinted at by unstable tectonic activity. Even video games like Subnautica build entire ecosystems around volcanic vents and shifting seabeds, mirroring the extremophile habitats scientists now study through seismic anomalies. These narratives tap into something primal, our instinct to fear, and explore the unseen. What makes these stories resonate isn't just their spectacle, but their metaphors. The seismic shadows in Godzilla vs. Kong aren't just plot devices. They symbolize humanity's arrogance in disturbing forces we barely understand. In Prometheus, a seismic survey uncovers an alien pyramid, a nod to how real archaeology uses vibrations to reveal buried history. Even children's media like Tremors or Atlantis, The Lost Empire simplifies seismic concepts into gateways for curiosity, asking young audiences, what if the ground beneath us isn't as solid as it seems? Behind every fictional tremor lies a kernel of scientific truth. When San Andreas dramatizes the Cascadia subduction zone's threat, it echoes real debates about earthquake preparedness. 2012's absurd crust displacement theory borrows from genuine seismic research on pole shifts and mantle plumes. These stories, however exaggerated, keep the public conversation alive, inspiring future geologists, funding for research, or even policy changes. After all, it was a Star Trek episode that first popularized the idea of tectonic plates shifting, years before the theory became mainstream. The most compelling tales don't just entertain, they reframe how we see our planet. Annihilation's shimmering alien zone, where nature mutates unpredictably, mirrors how seismic shadows reveal Earth's capacity for constant transformation. Interstellar's dying world, its dust storms fueled by ecological collapse, parallels real concerns about how climate change alters the very rigidity of Earth's crust. Even indie films like The Descent turn cave systems into psychological landscapes, echoing the claustrophobic wonder of actual subterranean exploration. Perhaps the greatest testament to seismic shadows' cultural power is how they've shaped mythology itself. Indigenous legends from the Pacific Northwest speak of Thunderbird and Whale, whose battles shake the earth, stories that align eerily with modern seismology's understanding of subduction zone quakes. Norse myths described Loki's tremors as the god struggled beneath the ground, while Japanese folklore attributed quakes to a giant catfish stirring in the mud. These ancient explanations, born from observation and intuition, weren't so far from the truth. They recognized what science now confirms: the Earth is alive, restless, and full of secrets waiting to be heard. From Verne's wooden raft on a magma sea to today's quantum sensors mapping mantle plumes, our fascination with the subterranean endures. Every time a filmmaker imagines a hidden world or a novelist conjures a civilization beneath our feet, they're participating in humanity's oldest tradition, staring into the dark and daring to ask what's really there. The answers, as seismic shadows show us, are often stranger than fiction. Think seismology is only for labs with million-dollar equipment. Think again. The same technology that once filled entire rooms now fits in your palm and costs less than a smartphone. Meet the Raspberry Shake, a compact seismometer that plugs straight into your home Wi-Fi. This little device detects everything from distant earthquakes to the rumble of passing trucks, turning your living room into a seismic listening station. Teachers are using them in classrooms to bring earth science to life, while retirees in earthquake-prone areas monitor local fault activity from their kitchen tables. The data, it feeds into global networks like the Incorporated Research Institutions for Seismology, helping professionals track quakes they might have missed. What makes this revolution so exciting is how it democratizes discovery. In 2021, a high school student in Oregon spotted unusual tremors on her homemade seismometer. Turns out they were foreshocks to a magnitude 5.2 quake. Over in Japan, a community group's DY detected subtle ground shifts months before the Kumamoto earthquake, patterns too faint for official networks to catch. Even urban gardeners are getting in on the action, burying sensors to learn how subway vibrations affect their crops. The barrier to entry isn't expertise or money anymore, it's curiosity. Setting up your own station is simpler than you'd imagine. Most consumer seismometers come pre-calibrated, with apps that translate vibrations into colorful, easy-to-read graphs. Place yours on a concrete basement floor or bolt it to bedrock for the clearest signals. Within hours, you might record quakes from the other side of the planet, their waves arriving like cosmic postcards after journeying through Earth's core. Some enthusiasts even collaborate online, forming seismic listening parties to analyze unusual signals in real time. Was that strange pulse a mind blast, a meteorite, or something entirely new? The ripple effects go beyond hobbyists. In Nepal, villagers now maintain low-cost seismic grids that alert nearby towns when traditional systems fail. California's Quake Catcher network harnesses laptop accelerometers, yes, the same ones that rotate your screen, to create an early warning mesh. And during the pandemic, lockdowns revealed something unexpected. Seismometers could track human activity, from the absence of subway tremors in New York to the resurgence of wildlife footsteps in Yosemite. Your backyard data might someday help predict the next big one, or inspire a kid to become the geologist who cracks earthquake forecasting for good. The Earth is always speaking. Now, more ears than ever are listening. Seismic shadows remind us that silence isn't empty, it's full of answers. Every gap in the data, every unexpected bend in a wave, is a clue waiting to be deciphered. These hidden echoes bridge time itself, carrying whispers from ancient earthquakes, lost civilizations, and even the birth throes of our planet. Imagine standing at the edge of a canyon and shouting. The way your voice bounces back tells you about the cliffs you can't see. Now scale that up to planetary dimensions, where every tremor is a shout and every shadow is an echo mapping the unseen. From the ruins of Helike, swallowed by the sea in an instant, to the slow creep of tectonic plates beneath Tokyo, these vibrations are more than just scientific data. They're stories. Stories of catastrophe and resilience, of continents colliding and oceans forming. They reveal how the dinosaurs met their end, how ice ages shaped our coastlines, and even how life might survive in the most hostile corners of our world. And the most astonishing part, we're only beginning to scratch the surface. The technology listening to these whispers is evolving at a breathtaking pace. What started with smoke-covered paper and swinging pendulums has blossomed into quantum sensors and AI-driven networks. Soon, we might predict earthquakes with enough warning to save thousands, or uncover lost cities without lifting a shovel. The frontier isn't just beneath our feet, it's in the algorithms that decode vibrations, the communities tracking quakes from their living rooms, and the next generation of explorers armed with tools we can't yet imagine. But here's the real question. What will we do with these discoveries? Will we use them to build safer cities, protect fragile ecosystems, or finally unravel the mysteries of our planet's birth? The Earth isn't just speaking, it's asking us to listen. So hit that subscribe button to join us as we keep uncovering these hidden chapters, and drop a comment below. What's the one seismic mystery you'd solve first? A lost civilization, the next big quake, or maybe something deeper, literally. The ground beneath us is alive with secrets. Let's find them together.